separation of charge. And that's exactly what I have on either side of the membrane. Okay, I've got a positive on one side and a negative on the other side of the membrane. So they are separated. And they are separated with a difference of approximately negative 70 millivolts. Okay, so our resting membrane potential is naturally more negative on the inside than the outside, out of a difference of about negative 70 millivolts. And so the negative means that the negative or the positive is referring to the inside of the membrane. So it's more negative on the inside of the membrane. If that was a positive 70, it would be more positive on the inside of the membrane. Okay, and so that's gonna be needed to start this. If we don't have the natural polarization, this isn't going to happen, because we need to have this natural difference in both concentration as well as electricity or charge, so that we can get movement of these sodium ions to carry on the action potential. So now that we've just established this charge, okay, let's take a look at what happens when we alter it and we get some of these sodium and potassium channels here to open up, okay, and see how that will actually help conduct the message. Okay, so in our resting state, remember we have this negative 70 millivolts happening here, okay, because of our membrane potential. And so now let's say a stimulus has come in. And so the dendrites receive that stimulus, and that stimulus gets integrated at the axon hillock, and that stimulus is strong enough now to open up some of these sodium channels. Okay, so here's a sodium channel. It opens it up now, and so sodium's going to go rushing in to the cell, because sodium has a positive charge, and the inside of the cell has a negative charge. And hopefully we remember that positive and negatives are attracted to one another. So sodium comes rushing into the cell. So if I have all these positive ions rushing into the cell, I'm taking away some of that polarity, that separation of charge. I'm bringing that separation of charge from a negative 70, I'm bringing it back towards 0, because I'm removing some of that separation of charge. So that would be what's called my depolarization. Okay, that's what I have happening here. So if I look at my graph over here, I had threshold, not threshold, I'm sorry. I had resting potential here, so we've got to be at about negative 70 millivolts here. And once I hit threshold, okay, once I've hit threshold, that means my stimulus is strong enough to cause an action potential. If I do not reach threshold, then there is no action potential. It doesn't matter. Let's give threshold a number. I think in your lab it's negative 55 millivolts. So let's say I reach negative 56 millivolts. Doesn't matter. No stimulus. The stimulus wasn't strong enough. No action potential will be formed. So threshold is basically how much it needs to depolarize or come closer to 0 so that it can make an action potential. So when these sodium gated channels open up and they come rushing inside, they're going to change the voltage. They're going to change that membrane potential. They're going to bring it closer to 0 and depolarize it. And so now we're coming up here closer to threshold. And once we reach threshold, that is going to accelerate dramatically. Okay? And we're going to actually end up polarizing the membrane again. What I have here is the rising phase of the action potential. So I reach threshold. There's no way we're not getting an action potential now, because once you reach threshold, you can't stop it. An action potential is happening. So there's no way you're not going to get to the action potential. And so that increase is going to happen very, very rapidly. And that's called the rising phase of the action potential. These sodium-gated channels are open. Sodium is flooding the inside of the cell, so it brought it up towards threshold and actually goes way beyond 0. Okay, and that depolarization, it doesn't just take it from negative 70 to 0, it'll go a little positive as well. It will continue up and make the inside of the cell a little bit more positive. And so once the peak of that rising phase has happened, we have created the action potential, it'll start to fall again. So the falling phase here of the action potential is going to be as it's dropping back down, and this is going to be due to these sodium-gated channels are now going to close. The change in membrane potential, taking it the inside more positive than the outside now, triggers these sodium-gated channels to close and triggers the potassium channels to open up. So now these potassium channels open up. Well, remember, potassium is positive. So now I've got all these positive ions leaving the cell. And so that's going to help electrically reset our membrane. Okay, it's going to cause that polarization to happen again. Okay, so in addition to the falling phase, it's called repolarization. I'm creating that separation of charge again. So again, it's called repolarization, or the falling phase of the action potential. And actually, when the cell is repolarizing, when the membrane is repolarizing, those sodium gates open. The sodium gates close and the potassium gates open. Okay, it actually is going to overshoot our normal resting membrane potential a little bit, okay, because those potassium gates cannot close. It doesn't hit -70 and they automatically close. So let's take a look at that. So when they overshoot, when those potassium channels can't snap close as fast as they need to, that overshooting there is sometimes called hyperpolarization. Because I took it, remember hyper is above or beyond, I took it further or past resting potential. I took it a little further than I normally would. And that sodium-potassium pump that we've looked at before, okay, that sodium-potassium pump, our membrane is now electrically reset. Electrically, these two look very similar. So it's electrically reset, but it is not chemically reset. And that's where that sodium-potassium pump comes into place. Okay, that sodium-potassium pump is going to be pumping sodium out of the cell to reset the chemical gradient there and pumping potassium back into the cell. And that's going to require energy to do that. Remember, that's a form of active transport. Now, once this action potential has launched, we have what's called a refractory period that happens after it. Okay? And so during the refractory period, in particular the absolute refractory period, there is no action potential can be formed whatsoever. It doesn't matter if it is the strongest, most intense stimulus that's ever happened. No action potential can be formed because the sodium gates are inactivated. Okay, they get inactivated while once they're closed and those potassium gates open. So these sodium channels become inactivated, and so you cannot create another action potential. If they won't open, you can't get that depolarization. So this refractory period, there is no stimulus can generate an action potential. And this is a short period. It's very temporary. It's just a temporary, like I said, temporary inactivation of the sodium gates. Okay, with the relative refractory period, a slightly stronger than normal stimulus can potentially cause the action potential, but it has to be stronger than normal. This refractory period also prevents the action potential from traveling backwards, back up the axon. Okay, axons are a one-way street. Okay, they only conduct these action potentials away from the neuron cell body, down towards the synapse, down towards the synaptic knobs and the axon terminals. And that's because of this sodium gate inactivation, this refractory period. The action potential cannot travel backwards. It can only go forward where there are sodium gates that are able to be opened up. So you can see here on this diagram how this action potential is only able to travel in one direction. Okay, so what I have here is this action potential causes the depolarization, and that depolarization of one portion of the membrane actually triggers the depolarization of the next portion. And while the original portion is going through its repolarization phase, it also is experiencing that refractory period where those sodium gates are inactivated. And so the action potential cannot go backwards, it can only go forward. So let's look at some ways that evolutionary-wise we've made this go a little bit faster. The faster we can send the message, the faster we can respond to the information that we have received. So there are two basic ways that an action potential can travel faster. The first one is the wider the diameter, the larger the diameter of the axon, the faster it's going to travel. But if you think about it, there's going to be limitation to size. Okay, limitation to cell size, limitation to body size. Our neurons can only be so fat and so wide, our axons can only be so wide and so large in diameter before they're essentially too big for our body. And so we have to look at different ways that we can speed up the action potential. And one of these is through what's called myelin. Okay, so the myelin sheath is formed by what are called, in the peripheral nervous system, formed by what are called Schwann cells. Okay, in the central nervous system, they're formed by what are called oligodendrocytes. And so oligodendrocytes and Schwann cells both do the same thing in the sense that they make this myelin sheath. Okay, and the myelin sheath is a fatty layer, and it's an insulator. Okay, so it insulates the neuron. Well, if you think about what you know about electricity and insulators, you know that insulators actually are not very good electrical conductors. But if you'll look at this, you will notice that the entire neuron is not myelinated. There's all these little, I don't know what that was. There's all these little spots that do not have myelin in them. Okay, and those are called our nodes of Ranvier. You can see one up close here. Okay, and so what this myelin does is it allows the action potential to essentially jump down the axon. Instead of having to depolarize every inch of that axon membrane, it only has to depolarize the areas that are not myelinated. And so it can jump, essentially, like I said, essentially jump. Okay, you can see that happening here, where it depolarizes this, gets to skip all the insulated part, and then depolarize the next node of Ranvier. And that is what's called saltatory conduction. Comes from the Latin to leap. Okay, think about it. If you were racing someone across the classroom and you got to take big giant leaps or jumps, and they had to shuffle their feet and touch every single inch of the floor, okay, well, obviously you, the one that gets to jump, is going to win that race. And so that's, like I said, this myelin helps speed up the action potential by doing that. Essentially allows it to jump over the insulated parts. And that's why things like multiple sclerosis, where it tears up the myelin and the neurons get demyelinated, that's why they have a lot of motor problems, because the messages aren't traveling like they should because of the lack of myelin. Okay, so I'm going to put a little video up that should take just a couple of minutes. That kind of sums up action potentials, resting membrane potential, and action potentials. And then we'll talk a little bit about the synapse, and we will be all set with this video. Okay, I'm going to try to get this video in here. Bear with me again. Still not very good at inserting the videos.
This baseball player springs into action, his nervous system rapidly processing information in a network of nerve cells, or neurons. Each neuron receives input from one or more cells. In response, the neuron may generate an electrical signal known as an action potential that travels down the length of the axon. Let's take a closer look at the plasma membrane of an axon. Even without an action potential, the axon is a busy place with many ions moving across its membrane. Much of this ion movement is driven by the sodium-potassium pump. Using energy from ATP, sodium-potassium pumps actively transport sodium ions out of the cell and potassium ions in, creating an uneven distribution of charge across the membrane. Some potassium channels are open all the time, allowing potassium ions to leave the cell. As a result of these ion movements, the inside of the cell is negative relative to the outside. This condition is called the resting potential. The membrane of an axon is also packed with gated ion channels that open and close during an action potential. At resting potential, the gated channels are closed. If a stimulus changes the distribution of charge across the membrane sufficiently, the gated sodium channels open. Movement of sodium ions across the membrane makes the inside of the cell more positive. This reversal of the charge distribution causes the gated sodium channels to close and the gated potassium channels to open. As potassium ions move out of the